right, well, welcome. So if you've read the program, you're probably looking at me saying, he doesn't look like MC Srivas. So I'm actually Phil in for today. Srivas unfortunately couldn't make it. My name is Jack Norris. I'm VP of Marketing with MapR. We're very excited to work closely with Lucid Imagination and the integration of LucidWorks and MapR, our distribution for Hadoop. What we have in this talk is an overview of some of the challenges with relating to integrating search, discovery, and analytics, and then some insight into some of those use cases. So before I start, I know earlier on in the keynote there was, raise your hand if you're using Hadoop, and there was, at least in my mind, there was a bit of a difference between 70% of the audience and the number of people raising their hand. So if you use Hadoop today, could you just raise your hand? Okay. What about kind of looking at it closely? All right, about 98%. Let me dig in. So first of all, these slides actually came from Grant originally as we looked at integrating Hadoop and search. And if you look at the evolution of search, starting with documents and queries, quickly expanding to look at user interaction and content relationships. So the real power of search and big data is at this intersection, right? And the exploitation of search, discovery, and analytics. And the combination of that to improve relevancy, to identify what's important, and to go beyond just simple kind of text and meta searching is really the key here. And our approach is from the analytics side. So I've got some overview slides here. I thought it was important to start with the obligatory big data slide. This one came from IDC, starting at 1.2 zettabytes in 2010, growing to 35 zettabytes. The important thing here is not the size. Really, the finding here, it's that data is growing faster than Moore's law. So it's not the absolute size, it's the rate of growth. The implications of this is however you're processing your data today, you're going to be doing it in larger clusters tomorrow. And the bottleneck now is really kind of pulling that data over the network. We've seen in many customer environments where it's taking longer to pull the data over the network than to analyze it in place. And what MapReduce, what Hadoop represents, is data on compute. So your data at rest, you're doing the computation, and you're sending the results over the network. And having search and discovery as part of that process, so you're identifying what's important and having the best results going over the network is really the key here. So if we look at MapReduce, it's this framework to make that distribution of the data so you can process it in parallel, make that very easy for the developer and ultimately the end user. This was a well-known concept, but MapReduce framework was really kind of pioneered and popularized at Google. And I think Google is probably one of the best use cases, kind of poster children for the power of MapReduce. We kind of take Google's dominance for granted, but when they came out, they were the 19th search engine on the market. And I don't think you could have been later. Right? You had Yahoo that was dominant, you had InfoSeek, Excite, AltaVista had TechCred, LookSmart, and there's a whole list of them. Here's this tiny little company in beta in 1998, and within 2 years, they were the dominant player. And it wasn't until 2003, 5 years after they were in beta, that they published a white paper on the MapReduce framework. And that gave us a glimpse into really how they accomplished it, how they were able to index much more data than anyone else, how they were able to get much more relevant results, and how they were able to do it much, much cheaper than the competition. And one of the people that read this white paper was an engineer at Yahoo, Doug Cutting, and decided he would take this kind of concepts and deploy it for his project around Nudge, and named it after his son's toy elephant, and that's really where we got Hadoop. It was this interpretation of the MapReduce white paper. So it's commercially available as Hadoop. We've seen this take off. There are different distributions and improvements, but the important thing, it's a very robust ecosystem to accomplish this result in this data and compute framework. The proof point here is in the job explosion. I thought this was interesting, not only showing the rate of growth, but if anyone is kind of questioning, should they pay attention in this presentation, there's a lot of self-interest, economic self-interest, based on the demand for Hadoop expertise in the marketplace, and the projections are this will continue to grow at a huge rate. So very briefly, one slide on how MapReduce works. So you take this data, the map function takes the data into small chunks, distributes that in parallel over typically cheap commodity servers. The replication factor is determined by policy. Do you replicate it 3 times, 4 times, et cetera? 3 times is typical. And each node is mapped, right? So there's a process to track where that is. When a project or a job takes place, then it's assigned to where the data is located. Typically it's assigned so it's running in triplicate, so that if there's a failure, you're still getting 2 other nodes that will report back results. The reduce function takes that, collapses it, and gives you the results. So the beauty is that whole framework, that whole management is part of that MapReduce or Hadoop framework. The programmer doesn't necessarily need to know and deal with the detail there. The other big driver of Hadoop is just the relative cost of the underlying storage. So rather than using network storage, SAN or NAS, you're using commodity disks, right? And the price points there are dramatically different. And then a use case here is that, what we're seeing is that Hadoop's being targeted for a large data store. I think the term in the keynote was a data refinery. Right, so the size of the data store kind of matters not only in terms of size, but also in terms of number of objects. We're billions and trillions of objects, and this is far beyond what the current limitation on Apache is, which is roughly 100 to 200 million files, which is a limitation of the name node. But the whole focus here is it makes more sense to perform analytics on the data and send those results over the network. So now let's get into the integration with SOLR and Hadoop. So it's relatively simple to integrate. It's a drop-down list in SOLR of, hey, I want to use HDFS as my data target. The difficulty is when you do integration at scale and handle distributed search. Now, SOLR Cloud kind of simplifies the sharding and replication, but you still have issues related to high availability, related to data protection, and related to kind of that ease of access. And let me go through an example here and kind of show what we mean by that. So here's kind of a simplified workflow. You've got input documents. Those are going into the map step. During the map step, kind of those documents are put into chunks and assigned to shards. The reduce step actually creates the index. That index is written to local disk and then loaded into or copied into the clustered index, and typically that again is copied before it's used by the search engine. And so these copies can take as long as the index itself, so you've got a bottleneck there. And the SOLR spidering is also impacted by the metadata operations supported by the name node. So you've got some areas of bottleneck, and you've got kind of this convoluted copy issue. There's also exposure during failures. So as you copy to local disk, if you've got some half-written file, that's a manual process to clean up. If you've got many indices, it's a manual process to kind of knit those back together. And if you're dealing with multiple locations, then you've got even more of a nightmare to deal with. So that's kind of some of the realities of the integration process. We're seeing some improvements on SOLR Cloud for the treatment of the shards, but that's separate than how the data is actually stored and accessed with Hadoop. And these failures kind of go back to the limitations of HDFS. So HDFS is the Hadoop distributed file system that's written in Java, and in turn, the HDFS stores its chunks in the underlying Linux file system in ext3. It's an append-only system, so it works like a CD-ROM. You write to it, and then if you have an update, it appends. You have to physically close the file before you can recognize the result. So, Hadoop's kind of referred to as a scratch-oriented, batch processing system. That's really an artifact of HDFS in terms of the scratch pad because of the lack of high availability and data protection for application and software errors. And the batch orientation, because of the append, you have to figure out what frequency you will close the file before you do the analysis on top. And that kind of relates to how we integrate that with the SOLR functionality, right? As you kind of expose the documents to SOLR, you want that SOLR index to be created and do that alongside of the Hadoop. There's also an issue of how you populate the cluster. So because the data has to be written through the HDFS API, right, typically what you see is a separate process outside of the cluster, or even a separate cluster in the case of Flume, where you're collecting data in that cluster and then writing that, uploading on a batch basis into the Hadoop cluster. So those are the limitations of HDFS. If we look at the requirement for this SDA, this virtuous loop of search, discovery, and analytics, ease of data access is a key capability, a key requirement, right? Because what we're looking at is how do we have these functions work closely together, and the ability to have the data easily shared across that is a key requirement. Related to that is the storage layer underneath that's used to house the data. How large can that be? What's its scalability attributes? How dependable is it? And then the ease of integration. Grant today talked a lot about REST. So you want the management layer to integrate with your other existing management layers, but it also extends to security, and it also extends to the type of analytics that are possible. So one area that we've looked at closely is this ease of data access. And the issue is that you want to have this data store present like Hadoop through HDFS, but simultaneously you'd like that to be treated and look exactly like enterprise storage. And if you can have a common data store that can be accessed by both, that simplifies things tremendously. It's that foundation that can be leveraged by not only the new kind of analytics that are possible with Hadoop, but also your legacy and existing systems. And if it's fully random read-write POSIX compliant, then you don't have to worry about changing the semantics of the applications or worrying about kind of debugging issues because you're not sure how it's going to function in a write-once-only manner. And while we're doing that, we also looked at limitation and looked at how do you scale this thing to trillions of files, not a simple file limit. Now what that does with the architectures that are possible is it gives you a lot of options, right? You can export that data source to the world and be accessed remotely through NFS. You can do that through a local server, or you can mount and have it export to itself. All right, so I know that was a lot of text, so I did a few diagrams to make that clear. So in the first example, you've got NFS servers that are accessing the data that's stored in the cluster. You've got any client that supports NFS is able to access it directly. You don't have to deploy any agents. You don't have any proprietary connectors. File browsers, standard applications are able to see and access the data directly, which is great. The second option, though, is instead of just having this client remote to the servers, why don't we put the applications directly on that server and access the data directly from the application that's housed in the cluster. Eliminate that middle tier, do it much more simply. But we can go beyond that and we could actually have the application running on the cluster node itself in the Hadoop cluster, mount that local storage, and it's actually faster than accessing the local file system itself. So going through this kind of NFS local mount is faster than ext3. And when you do that, you can also access all of the data through the cluster through that local mount. So this capability makes the integration of SOLR and Hadoop much, much cleaner, much easier. So let me show you how. So now we've got this input process going to the map, going to the reducer, going to the cluster index storage. There's no separate copying. There's no separate process. If there's any sort of failure, that failure is cleaned up by the MapReduce framework because we haven't copied to a local source outside of the framework. So we get two big benefits with that. Number one, we get this close integration of the kind of search process, SOLR and Hadoop. And number two, we get SOLR that benefits from all of the high availability capabilities of the cluster itself. So how does that integration happen? Well, the first point is that it's elegantly simple. And that's usually a very good thing. And it's a result of the architectures, right? So you basically have data that's being written directly into the cluster, written to a volume, and you've got SOLR saying, I'm going to index everything that's written there. And because that data is being written and can be accessed through standard interfaces, there's no copying that has to be done, there's no changes to SOLR, it's just accessing and the crawler is creating that index. And then once that index is built, you have end users that can access SOLR and search the contents of the cluster. And the search that they are performing is based on what's been crawled. So there's no time lag depending on when there was an upload, or there's no synchronization process to say now we've got to get Hadoop updated to SOLR, and then, or SOLR kind of exporting the indices back to Hadoop. And later on, when we get to how this improves relevance, the impact of this will be hopefully even more clear. So there is a slide here to talk about distributed shard indexing, and hopefully I can do it justice. But basically what happens is your input is produced into small chunks, and those chunks during the map step then are assigned to shards. And there's a process then that takes those shards as input into the reduce step, and the output of the reduce step is the index. And there's a combination step where you can take shards that are across and kind of reduce those. There's not a one-to-one relationship. And hopefully this makes it a little bit clearer, but you've got documents. And those documents then are assigned to shards and kind of assigned randomly. So shard 1 can have elements of doc 1 and shard 2, doc 2, but shard 1 could also exist or also have elements of doc 3. And then when you look at the index or the reduce step, it's taking all those shards, combining those together, and then producing the index. So in this process, we can have the MapReduce function produce these indices. SOLR can use these indices, and then Zookeeper can be used to manage the various SOLR instances that exist within the cluster. And this supports a large distributed kind of search formation using SOLR and Hadoop. And there are other ways you could do it. I was talking with Grant, and you could take the map function and have the map function feed SOLR and have SOLR do the reduce step and create the indices there. So there is flexibility. This is just one example of how that's produced. Now the advantage of that, we've got SOLR running in the cluster itself, so all of the data protection features that are in some of these advanced Hadoop distributions, and of course I've got some self-interest representing MapR, but there are a series of kind of HA and data protection capabilities that are part of that cluster that then SOLR inherits because it's running in there. and includes things like rolling upgrades and self-healing to snapshots and mirroring and checksumming and business continuity. So this is kind of the list of features. How that works can range depending on what's processed. So here we've got an example where we've got a MapReduce. It's a failure to write an index. And as it exists today, you have that issue of a half-written index. Because we're running that within the cluster and it's integrated, MapReduce basically cleans up those partially written indexes. There's no administrator intervention that's required. You've got a fully highly available job tracker and task tracker. So if the job tracker fails, it just picks up where it left off on another node, maintains state, and completes that process. So the whole focus here is the kind of clean, manual administration-free process. So what happens if the SOLR node fails? Well, we've got SOLR running on multiple nodes, indexing across multiple volumes, and if one of those node fails, then the zookeeper alerts this other SOLR to do the indexing on the replicated content that's on that volume. Again, kind of inherits the capabilities of the cluster, leverages zookeeper. What happens if the node containing the index fails? Well, similar type of process. Data is already replicated across the cluster. Zookeeper assigns a SOLR instance that has that shard on that node to start the process there. So there's some additional high availability capabilities as well, including snapshots. Snapshots are useful to handle user issues, right? So, gosh, we've made a mistake here. Well, I can roll back based on the snapshot frequency. You set the frequency, whatever makes sense. You can do that at a volume level, so it's not a cluster-wide policy. You can have volumes by project or different data sources or use cases or users or what have you. And that's a hidden directory that you can restore single files or entire directories. I think some of the first questions on snapshots typically are, look, I've got a petabyte of information in this cluster. How much additional storage do these snapshots take? And it's a redirect on write. So it's basically a pointer keeping track of when the blocks are written. And if the change rate is low, there's basically no storage penalty whatsoever, and you can do snapshots every minute. And it works the way kind of enterprise storage typically works today. Related to that is mirroring support. And with mirroring support, you can mirror within a data center. So you want to go from a production to a test or dev cluster, and you can do that by selected volumes. It can work across data centers. It can work from an on-premise to a cloud. So basically, this is part of a larger DR strategy, and it keeps the data in sync and eliminates a whole host of manual issues or manual tasks that would result if there was any sort of downtime or interruption. So, what does that simplified data flow look like? Well, same process, but then you can have mirroring, and that mirroring can be for DR purposes, but it could also be for performance reasons as well. So, we kind of just reviewed how SOLR and Hadoop work together. Now let's kind of focus in on this continuous feedback loop, right? So really what we're looking at is how can we improve the quality of search results based on end user activities, right? And how can we automate that process that doesn't require any sort of manual tags or manual work to improve those results? So sometimes this is referred to as collaborative filtering. But we're looking at actors or users that interact with items, and based on their behavior, injecting that back into the search process. So, and improving, quote unquote, successful interactions, right? And those successful interactions can be a host of things. Here's just a few kind of consumer examples, whether it's buying books and having book recommendations, or rating music or movies, or a successful interaction would be not skipping a song as they're listening to, internet radio, or not bailing out in the middle of a video, right? All those kind of represent quote-unquote successful interactions. And it's also using recommendations. So a query for friends will turn up links to Seinfeld. Or if you're searching for, this one kind of kills me because our chief application architect tested it, but you could search for kittens and actually find pictures of baby otters. All that is a result of other people's interactions and using that to come up with better recommendations. So there's some, math here, and I've kind of truncated some of that, but instead of a dyadic structure that's kind of driving this, you can expand well beyond that, right? And the whole focus is on how you use co-occurrence to improve the search results. So we've got, users who interacted with X also interacted with Y, but we want to go beyond that and take information from not only user queries and what resulted in a successful query, but also user behaviors. So here's an example where we've got A and A prime of user queries, right? So we said, well, did you mean this query? But we can also have recommendation engines, right, based on, users B and B prime that, view these videos, also view these videos. But the real power can come when we can mix across and use B prime A, which is basically in response to a specific query, show a video recommendations, right? So it's the best way to kind of summarize this. It's search engine-like, but it's really unlocking the power of this search, discovery, and analytics, right? Relatively kind of focused, simple example, but it's how do we kind of go beyond and really identify what's important to the end user. One real-life example is this query for Paco de Lucia, which is a flamenco guitarist. In conventional metadata search, you do that search and you get a lot of guys named Paco. If you do a search that's based on recommendation engines, you find a whole host of related items, including my favorite, Van Halen doing a flamenco classical guitar riff. And ultimately, that's the goal of this kind of linkage of search, discovery, and analytics, right? Is how do we kind of tease out of the data, how do we automate this process so that we get much more successful results given sparse interactions? So basically this quest for relevancy, it's about big MapReduce jobs to take disparate information sources. We've talked a lot about log files, but it can go way beyond log files. It can be mixing up transaction information with social media information, with other content, and use that to improve results. And one of the hidden factors here is Google did a paper called The Unreasonable Effectiveness of Data. And it was written by 3 directors, and it was in the area of natural language processing. And it was a takeoff on a paper called The Unreasonable Effectiveness of Mathematics, which was showing in the physical world how very simple equations can be used to powerfully explain natural phenomena. Like E equals MC squared is probably the first one to jump to mind. And in this article, these Google directors were saying behavioral economists always were kind of envious of that. But what they found with their work with natural language processing is that relatively simple algorithms that prove to be completely ineffective given certain data sets, when you expand those data sets, they start to become strikingly effective. And in the paper, they used the example of pixel completion. And they didn't call this out, but I think it's from the whole kind of Google Street View, where they want to selectively take things out whether it's users in their underwear in their front lawn, or cars or whatever. And they have a simple algorithm to do that. And if you have a corpus of hundreds of thousands of files and you use this, it's very clear that there was something there in a shape, and it just doesn't work very well. But when they increase that to millions of photos in the corpus and use the same simple algorithm, it was strikingly effective. And that's, I think, what we'll see really be a focus for big data, where simple algorithms on big data beat complex models every time. And that's what's really driving this kind of virtuous loop with search, discovery, and analytics. And the power of this loop is really a function of the ease of what I termed here frictionless data access, frictionless high availability, and frictionless performance. If these things work really well together, and you can have the data being fed and the user interactions so that the search and discovery continues to provide additional insights going forward, then it simplifies everyone's job, primarily yours. So we've got just a few minutes left. Are there any questions?
So in the traditional enterprise search model, they would show your source document, your pipeline, and your search index. And I was wondering, with the MapReduce piece, where does that pipeline fit in? Is that part of reduce, or is that part of, how would I pre-process information before I put it in?
It's probably related to this. This is your source kind of input documents, right? That's kind of your pipeline. And then the map function kind of creates those chunks and assigns it. And really, you've got multiple ways to approach this, right? You can use MapReduce or Hadoop to create the index, right? And I think that's what Grant referred to earlier today as bulk index creation. But you could also use SOLR somewhat independently, where data is just being fed into the Hadoop cluster, and the index is happening on SOLR by looking and kind of reading that directly, and then having those series of indices kind of work in concert, kind of above with a zookeeper-like structure. And then there's the kind of hybrid where you split the map and reduce function, and I'm not as aware of that, but that's an area that Grant's team has been playing with some of their work at Lucid.
Does that mean you're still sharding and somehow sharding the index, and therefore you're searching in a small portion of the index in that machine, so you don't have the scoring too long?
Yeah, great question, which probably has multiple answers, but there is kind of an approach where you've got a series of sharding, sharded indexes, and you've got a distributed search going on where there's search going on across multiple indices, and then the result set is kind of aggregated. All right, thank you very much.